Go ahead, Dave.
Hey, thanks a lot. It's a pleasure to be speaking at this meeting. I don't know, Dana, who came up with the title for this talk? This is a very ambitious topic to be talking about. And when I was putting together my slides today, what I realized was basically that we don't know. That's the simple answer to this question. There's two things we don't know about on the moon. One is we don't really know what the volatile distribution on the moon really is. During the earlier part of this meeting, we saw some talks by Carly Peters, by Tony Colapri, showing that we've got some evidence as to what this volatile distribution is, but most of the moon's volatile distribution remains somewhat mysterious. And then you add to that we don't fully understand all the processes that control the moon's volatile distribution. So you put these two facts together, and you end up with a fairly murky situation in terms of our understanding of these particular problems. So the next question becomes sort of how to attack this problem. And in my talk, I'm going to highlight sort of two areas that do potentially provide some insight. And these come from first looking at what's going on with recent observations that we have on Mercury, and then also talking about some new lunar data that we have that also may be relevant to this problem. So don't expect a complete answer to the whole volatile question from this talk. So the basic underlying concept that underlies most of our study of volatiles has to do with the concept of cold trapping, which was first proposed back in the early 60s. Here's a paper by Watson, Murray, and Brown in 1961 that basically describes the idea, which is that in regions of at the poles of the moon that don't receive direct sunlight, there could be very cold places, places that are as cold as they are in the outer solar system, where ice is thermally stable to evaporation. And the idea is basically that if you have niches or cold-trapped areas that could be cold enough to trap water ice, and if there were a supply of water ice, and that's a big if, or water in some form, you could cold trap it there, along with a range of other volatile materials. And here's some early work that shows sort of the range of temperatures that you might expect to cold trap volatiles. This basically remained a theory throughout the Apollo era, and it's only sort of, over the past couple decades where data has come in that has now basically shown that this idea is correct, although all the details regarding it still remain somewhat mysterious. Now, if we take the case of Mercury, we can calculate using topography data now provided by Messenger, as well as thermal model calculations which match what we can see with Diviner on the moon, fairly accurately what the temperatures should be on the surface and subsurface of Mercury. And this is some results from a recent science paper that show the biannual maximum temperatures on the surface of Mercury. And you'll see in here that there's a tremendous range of temperatures that are exhibited, all the way temperatures, in the order of 550 Kelvin, down to temperatures that are below 100 Kelvin. This is the maximum temperature that's achieved on the surface. And you can see in some of these craters, larger craters near the poles as well as the surrounding area, lots of places that ought to be cold enough to cold trap water ice. The key question, of course, is this is not much more than a fancy version of Watson, Murray, and Brown. It's basically saying, okay, yeah, it's cold enough there, but the question is, are the volatiles actually cold trapped? And this comes from other types of data. The first and still and essentially the most definitive data we have for the Mercury cold traps containing water is the radar observations. This is an example of an Arecibo radar backscatter image that shows very bright depolarizing radar signals which imply the presence of lots of ice, like meters of ice, on the surface or below the surface. Since these data were obtained, we've now orbited the planet with MESSENGER, and we have 3 additional lines of evidence that show that these deposits contain water ice. One comes from the neutron spectrometer on MESSENGER, which shows a definite signal indicating enhanced hydrogen abundances associated with Mercury's polar deposits. And then we also have measurements from the MLA instrument, the laser altimeter, which has measured at the reflectance of the surface at 1.1 microns in the polar regions. This is the plot where we've, in the background, it shows thermal model calculations as to where water ice ought to be stable both on the surface, as indicated by these white areas, and below the surface, as indicated by these color areas. Basically, water ice is stable above and below the surface at a range of spots. Turns out these correlate exactly where the radar observations show that the presence these anomalous backscatter deposits. So that's very exciting. The last piece of information comes from these MLA observations. Here we've correlated annual maximum temperature predicted by the model for the surface on the x-axis and the MLA reflectance on the y-axis. This shows that, average mercury at this wavelength, at this observing geometry, is about 1.15 albedo. As you get towards colder temperatures, the albedos drop. And then right as you get to about 100 K, which is about the temperature that we'd expect to find stable cold-trapped water ice, the albedos shoot up. And what we're seeing here basically is MLA detecting actual surface ice that's bright on the surface, which is very exciting because for you to find bright water ice on a surface like Mercury, it means that it must be fairly recently deposited because there's a bunch of processes that will tend to darken the ice, eliminate the ice, or bury the ice over time. So as far as we can tell on Mercury, we have an active supply of water ice that can overcome whatever ice destruction processes are occurring. And it appears to be distributed basically exactly where it would be predicted to be thermally stable. So all these point to a very nice, set of reinforcing observations in theory that we sort of know what's going on in terms of Mercury, which is, of course, very gratifying. Now, if we turn our attention to the Moon, we have a rather different situation. This is a set of measurements from the Diviner Lunar Infrared Radiometer on LRO. We've been orbiting now the planet for a period of more than 3 years, and we've obtained very detailed maps now of measurements of the thermal behavior of the lunar surface. This is a map of the North Pole annual maximum temperatures, and for some unknown reason, it's a cutoff map of the South Polar annual maximum temperatures. Elliot Sefton-Nash of UCLA is going to be giving a talk next about these results, and so I'm not going to dwell on them. But the main message is we've got measured temperatures, and we see that, in general, the Moon is quite a bit colder than Mercury, mostly because of the fact that it's further from the Sun. And the models and data suggest, at least from the thermal standpoint, that there ought to be very widespread niches for water, ice, and other volatiles on the Moon. And the question is, what can we see from other data that might indicate that it might be there, especially given that the basic theory has been proved on Mercury? Well, unfortunately, the data that we have don't all point to the presence of extensive volatiles, nor do all the data sets that we have necessarily agree with each other currently. This is a Earth-based circular polarization map of a ratio map of the lunar south polar region. If this same map were of Mercury, you'd see these enormous bright water ice deposits in all the places that have permanent shadow. But we don't have any such strong signals coming from radar observations from the moon at any of the wavelengths that have been observed yet. As was described earlier, we also have neutron spectrometer observations that also point to the presence of enhanced deposits of hydrogen. These come both from Lunar's prospector and from LRO from the LEND instrument. However, if you were to look at Mercury or Mars, for instance, which also has extensive ice deposits, these signals would be quite a bit more extensive and brighter. The detection of ice is fairly marginal by the neutron experiment, suggesting either it's concentrated in small regions that are way below the resolution of the instrument, or it is below the depth that the instrument can sample, or simply it's not there. And there's also measurements by the LRO LAMP instrument, which have also been touched upon, that show that there's dark regions in the ultraviolet associated with some of these permanently shadowed craters. Here's a picture of LAMP Lyman alpha albedo. And there's also some spectra from LAMP that also suggest the presence of surface water ice ultraviolet spectral signatures as well. This is a very tantalizing observation. And again, it's got to be mixed in with all the other types of data that we have. In the time I have remaining, what I'd like to do is highlight a new data set that's been sort of worked on by the LRO Lola team. As has been shown previously, Shackleton Crater had been shown to have anomalously high reflectance in the near-infrared from the Lola observations at 1.1 microns. Since these original data were published by Zuber et al. Last year, the Lola team with Paul Lucy and Miriam Reiner have been working very hard to basically recover and calibrate a much larger data set for both polar regions. And we're currently sort of looking at these data from a variety of perspectives. This gives you an idea of what this data set actually looks like. This is an interpolated view of Lola albedo in the south polar region. This goes to 70 degrees south latitude. You can see a number of bright and dark areas here in this representation. This big bright thing here is Shackleton Crater, but there are other bright features at other latitudes and locations. Bright features are associated with recent impact events that have exhumed unweathered material. They're also associated with mass wasting down slopes, which also exhume unweathered material. And what we're looking at is whether or not there are also some of these bright signatures in the polar regions that may be associated with the presence of at least partial cover of bright material associated with surface volatiles. The real good way to do this is to basically cross-correlate the Lola reflectance data with the Diviner brightness temperature data, which is sort of analogous to what we did on Mercury, which yielded such clear results. And we're in the process of doing this, and I'll show you sort of what we have so far. Here's a scatter plot that shows albedo as a function of Diviner channel 8 maximum annual brightness temperatures in the north polar region as an example. This gives you a general idea of the character of the data. The Diviner data are sort of bimodal along this axis. There's cold, permanently shadowed areas and then non-permanently shadowed areas. And then there's a range of reflectances that are observed by Lola. What I'm going to show next is an exercise where we sort of thresholded the Lola observations to just sort of look at the proportion of them that are higher than usual based on this average as a function of temperature. So this is a way of sort of identifying if there's any real temperature dependence to the Lola reflectivities. First, I'm going to show for the south polar region, the annual maximum temperature on the x-axis and the average Lola albedo on the y-axis. And you see here that there's a pretty clear trend of increasing Lola albedos with decreasing temperatures. This trend, though, extends to very high temperatures as well. And the current thinking is that this is not going to be purely due to volatiles, but in fact a space weathering effect. The idea is that as you go to lower temperatures, you're also correlating that with lower input of solar energy, potentially solar wind, and other sort of factors. Santala wrote a paper way back on the idea that as you get colder, you're going to produce less melt when small impacts occur. All those factors tend to darken the planet. So the fact that you're getting brighter soil as you get to lower temperatures, I think is understandable in terms of a space weathering effect. The key question is...
2 minutes left, Dave.
Thank you very much. The key question is what's going on here as you get to the coldest temperatures and the highest albedos. Is this now a volatile effect? We can look at the fraction of high albedo Lola points, in this case greater than 0.38 albedo, in the south polar region as a function of temperature. And this produces a very interesting set of curves here. Basically, there's a very small fraction of the Lola points that are unusually high albedo at these higher temperatures. But then as you get into these lower temperatures, you find these interesting peaks and valleys, and most excitingly, a peak right here at 100 Kelvin. So it's saying that there are a greater proportion of bright Lola peaks at 100 Kelvin than at any other temperature. And the question is, what does this actually mean? Paul Lucian produced this plot that shows normalized histograms of temperature of Lola albedo as a function of temperature. So you can follow sort of this peak here. And these bumps here, which sort of come right out at 100 Kelvin or in the vicinity of 100 Kelvin, are indicated at both poles. And what we're wrestling with is, all right, is there any way that we could explain this unusual bump here that's correlated with temperature by anything except for something that might involve, surface volatiles? And so far, we're sort of optimistic that this is going to pan out. What it means is, still anybody's guess. There are lots of ways to brighten surfaces with volatiles. Either you could have a thin layer of recently deposited pure ice, maybe fine grain, maybe not uniformly over the pixels, that could give you a high albedo, or you could have a much greater proportion of ice that's intimately mixed, let's say with dirt or soil. In this case, to get a bump like this, we would be sort of looking at the tip of the iceberg, so to speak, with regards to sort of older ice that may have been, deposited below the surface and is gradually getting overturned and exhumed by more recent processes, in which case this would hint at a much larger reservoir of ice that's mixed with dirt. Therefore, you don't have the radar signatures, and maybe much of it is buried deeply, and therefore you don't have the neutron signatures. But again, we're not quite sure about all this, and there's a lot more data to look through. So I think in light of the time, I'll quit there and open it up for questions. And thank you very much.
Thank you. All right, thanks, David. And while we're waiting, I think there was Gordon Chin asked a question.
I see Gordon Chin's question. Do we know if the comet impact, is enough to balance the destruction of ice on the surface? Well, yeah, I mean, this is a problem we have on Mercury as well. The question is the is the ice that we're seeing due to sort of, the superposition of a bunch of sources of water from the moon, be they comets or asteroids, or is the ice that we're seeing sort of a lucky fluke? In other words, that a large comet has recently hit the object and deposited ice very broadly. I don't really know if we can say one way or another what's going on here. In other words, is the difference between Mercury and the moon just a question of pure luck? And if we came back and look at the moon in 1 million years from now, would we see, a lot of water deposited on the surface if there was a recent impact? Completely overrule the recent impact. But if the Mercury situation is like that, you might expect to actually see evidence of that crater at some point. The answer to your question, Gordon, is I don't know.
And David, to be clear, Gordon had asked earlier, what is the source of water that could resupply the Mercury ice David Goldstein gave was comets. So
yes, possibility, but about the the lunar interior water, and from lunar sample analyses, and obviously getting enough information about these lunar polar deposits as well as the Mercury ones to understand their isotopic ratios would be a huge, huge, huge clue, obviously. Future observations.
Okay, thank you.
Thanks.